All right, continuing on with section 3, which is oxidation-reduction reactions, or more commonly referred to as a redox reaction. Before we talk about what redox reactions are, I just want to remind you that redox reactions are not a seventh type of reaction. If you remember from topic 9, we talked about the 6 types of reactions. Redox reactions are not a seventh type of reaction, but instead you notice it's right here. These 4 types of reactions all fall under the category of what a redox reaction is. So you have single replacement, combination, decomposition, and then combustion. These 4 are technically also known as redox reactions. And we're going to talk about why that is in this video as well as in the video next. So what is a redox reaction then? A redox reaction is a chemical reaction where electrons are being transferred from one reactant to another. So let's say, for example, I was taking solid sodium and reacting it with fluorine, right? So those are our reactants. What ends up happening in this example is sodium would actually donate its electron to fluorine, resulting as a product, sodium would now be positive and fluorine would now be negative. Okay, so redox reactions are just simply electrons being transferred, but the key thing to note is that what happens? The charges are changing. Sodium was originally neutral, now it's positive 1. Fluorine was also originally neutral, now it's negative 1, right? So charges change in a redox reaction. So in order to be able to navigate a redox reaction, we need to be able to assign charges to every single element so we can see how they're changing from reactant side to product side. If you recall back at the beginning of the semester, I taught you some tricks to be able to figure out what the charges are for elements, right? And we wrote those at the top of our groups in our periodic table. Unfortunately, those are just trends. So there's some rules that we need to be familiar with so we can assign oxidation numbers or oxidation states, which really, for all intents and purposes, is the same thing as charge. Okay, so before we go through these rules, I want to review some rules that we've already learned that still hold true. So first of all, if you are looking at a group 1A element like lithium, sodium, potassium, things like that, they are always going to be plus 1. Okay, that's not changing. Alkali metals will always be plus 1. If you're looking at a group 2A element like calcium, beryllium, your alkaline earth metals, those will always be plus 2. And then finally, aluminum will always be plus 3. So those still ring true. Notice I say just aluminum. I don't say group 3A because there's actually some exceptions in that group. So just aluminum will always be plus 3. Now, in addition to this, that's where the rules come into play down below. So let's review them. Rule number 1 right here. The sum of all the oxidation numbers in a neutral compound should equal 0. And the sum of all the oxidation numbers in an ion should equal the charge for that ion. This actually isn't anything new. You should hopefully already be familiar with this. So for example, if I was looking at water and I wanted to, what's the charge of hydrogen? What's the charge of oxygen? Well, water is neutral. So whatever their charges are individually, whatever their oxidation numbers are, it should all add up to be 0 because water is a neutral compound. On the other hand, if I'm looking at sulfite, SO3, which is a -2 charge, well, everything should add up to be -2. Okay? We'll revisit that, but that's a good rule to start with. It keeps us in line with everything else. All right, keep on going. The oxidation number of any neutral element is always going to be 0. So for example, if you saw just regular sodium, or even the oxygen molecule, if I asked you what are their oxidation numbers, it's 0. The oxidation number of a monatomic ion is equal to its charge. This one actually, this should be intuitive. So if you see calcium 2+ written in a chemical equation, then its oxidation number is +2. Okay, that's very straightforward. All right, the oxidation number of the more electronegative atom in a molecule or complex ion is the same as its charge if it were an ion. Let's break that down, right? Because that's a little confusing. Let's look at the compound nitrogen monoxide, right? Okay, nitrogen monoxide is a neutral compound. It should be equal 0. Well, under normal regular circumstances, what would you say is the charge for nitrogen? It's -3, right? Okay, under normal circumstances, what's the charge for oxygen? -2. Okay, well, do -3 and -2 add up to be 0? No, they don't. So one of those elements, either nitrogen or oxygen, needs to be different. So which one is it? The rule states that the more electronegative element gets to keep its normal oxidation number. So out of nitrogen and oxygen, oxygen's more electronegative. So oxygen gets to continue being -2. So what then must be the oxidation number here for nitrogen in order for this whole compound to equal 0? The oxidation number of nitrogen in this particular compound must be +2 because there's one nitrogen and one oxygen, and together they have to equal 0. And that's what you see over here to the right. So that's the rule there. If the more electronegative element gets to keep its normal oxidation number. Okay, oxygen is probably the most common element you'll see pop up all the time. So it's good to know the oxygen rule. Pretty much oxygen is always going to be -2. I would say 95% of the time, if not more, oxygen will be -2. But there are some exceptions. If oxygen comes in a peroxide form, which, how do you know it's a peroxide? You'll know it's a peroxide if it's a cation bonded to O2. Okay, so when you see O2 bonded to a cation, then O2 is actually the peroxide ion. And peroxide, O2, is -2 as a whole. So if you have two oxygens bonded together for a total of -2, what's then the individual oxidation number of each of those oxygen atoms? Well, -1, right? So that's an exception there. If it's a peroxide, then oxygen will be -1. Like in this example right here. You see how you have you see how you have sodium bonded to O2? That O2 is actually a peroxide. So that's one exception. The other exception is if oxygen is bonded to fluorine, right? Because fluorine is more electronegative than oxygen is. So in the case of, let's say, for example, OF2, right? OF2, well, fluorine always gets to be -1 because it's the most electronegative element on the periodic table. So based on this rule we learned up here, fluorine always gets to be -1. Well, if OF2, which is a neutral compound, if fluorine is -1, then what must be, and you have two fluorines, so two -1s, what must be the oxidation number for oxygen? So that total, it's a neutral compound. Oxygen must be +2 in this particular molecule, and that's where you get +2 there. The final rule is hydrogen. Hydrogen's oxidation number is always +1, except if it's a metal hydride. How do you know it's a metal hydride? Because it's a metal bonded to hydrogen, and then that's it. So hydrogen will always be +1 unless it's like, for example, you see how you have NH? Well, that's a metal hydride. Sodium always gets to be +1. So what then is the oxidation number for hydrogen here in order for it to equal 0? Must be -1. So that's an exception there. Okay, at this point you're probably thinking, this is not making a lot of sense. And I get that. It might be making a little bit of sense, but maybe it's kind of hazy. Let's look at some examples and see if that helps. Okay, what we're going to do in example 5 is I'm going to give you a compound or an ion, and I want you to assign the oxidation number for every single atom in the following. So let's take a look at SO2. Okay, so SO2, what I want to know is what's the oxidation number for sulfur, what's the oxidation number for oxygen. Okay, and remember, oxidation number is just simply charge. Okay, all right. To do that, I first notice that its SO2 is a neutral compound. So no matter what they are, everything has to add up to be 0. Keep that in mind. All right, so I asked myself, do I know a rule for either sulfur or oxygen? I do not know a rule for sulfur. There was no rule that we went over on the previous screen for sulfur. But there is a rule for oxygen. And the rule was oxygen is always -2 unless it's bonded to fluorine, which it's not, or unless it's a peroxide. This looks like it could be a peroxide because it's O2, but sulfur is not a cation. So this is not a peroxide example. And so the oxidation number for oxygen is -2. So now what's the oxidation number for sulfur? We need to do a little math to figure out what it is. Oxygen is -2, but you've got two of them. So total, it's -4, right? Between the two of them. Well, whatever the total is for sulfur, plus the -4 total for oxygen has to equal 0 because SO2 is a neutral compound. So what plus -4 is going to give you 0? The answer to that is +4. Now that's the total for sulfur. We're asking what's the oxidation number for sulfur. So we have to think, okay, that +4 is divided up over how many sulfur atoms? Well, there's only one sulfur atom. So that +4 is divided up over just one sulfur. So that must mean the oxidation number for sulfur is actually positive 4. So that would be the answer there. Let's take a look at NaH. What's the oxidation number for sodium? What's the oxidation number for hydrogen? Well, sodium is always +1. It's an alkali metal. And therefore, if this is a neutral compound, what's the oxidation number for hydrogen? It's -1. And think about that. That goes right in line with what we learned. Hydrogen is always +1 unless it's a metal hydride. In this case, it was. Let's do one more together. Let's do CO3, -2. This time, the carbon and the oxygen have to add up, not to be 0, but it has to add up to be -2. So do I know a rule about either carbon or oxygen? I do know a rule for oxygen. Oxygen's always -2 unless it's bonded to fluorine, which it's not, or a peroxide, which it's not. So oxygen's -2 here. And like I said, oxygen is most likely always going to be -2. Just watch out for the exceptions. Okay, now oxygen's -2, but notice there are 3 of them. So what's the total for oxygen? -6, right? Well, what's the total for carbon have to be if when you add them up, you end up getting a -2? Because -2 is the total here, right? So these two added together should equal -2, not 0. Well, it would be +4. And that +4 is divided up over 1 carbon. So +4 must be the oxidation number for that carbon. We're going to do this last one in the next video.